Alright, to start with section 2, we're going to look back a little bit to section 1 and an exponential function in this form, 2 to the x. If we were to sketch a graph of this, first off, understand that the domain for any exponential function would be all reals. The range for this exponential function would be everything greater than 0, which makes an asymptote of y equals 0. If you were to put coordinates in, if you substitute a 0 in, you would get 1. Substitute a 1 in, you would get 2. A 2 in would be 4. A 3 in would be 8. A 4 in would be 16. If you substitute a negative 1 in, you get a half, and then a fourth, and then an eighth, and then 16, and so on and so forth. And so our graph of an exponential function would look like that. And so now, section 2 deals with the inverse of that particular function. So if you recall from chapter 1, finding an inverse, all you do would be switch the x and y values. So instead of the coordinate 0, 1, you would now be at 1, 0. Instead of the coordinate 1, 2, you would be at 2, 1. Instead of the coordinate 2, 4, we would go to 4, 2. And instead of 3, 8, we would be 8, 3. 16, 4, and so on and so forth. So at a half, we'd be at a negative 1. A fourth would be a negative 2, and so on and so forth. And so it's going to run along the y-axis until it curves and goes over. Let's put this one in the right place first. And continue on in that direction. Now, this function, as you look at it, the domain is everything greater than 0. The range would be all reals, because you can get any real value here. And the asymptote is now going to be x equals 0. This function is called a logarithmic function. I can hear the groaning now. In a logarithmic function, it is the inverse of an exponential function. The domain is greater than 0, the range is all reals, and the asymptote is x equals 0. So let's look at this logarithmic function in a little bit more detail. To write it, you would write log with a little 2 here as the base, and then this would be x. And either write y equals or f of x equals. Now, looking at that expression, you need to understand that the 2 represents the base of the logarithmic function. So it's log base 2. The exponent, if you're going to rewrite this f of x or y is the exponent. And this x is what it equals. So all this means is 2 to the y equals x. except usually you're trying to find out what the exponent is, so you have to use a logarithm to figure that out. And within the logarithm, as we just stated, the domain is all greater than 0, the range is all reals, and the asymptote is x equals 0. Now, just like with any other particular function, if we want to sketch the graph of something like this, then what is the x plus 3 going to do for our graph? Yes, it is going to shift it left. Three spots, or 3 places. So now, looking back at our graph, it would take all of these coordinates and move them left 3. And it would be this graph. Now our domain would change to everything greater than a negative 3, and our asymptote would be x equals a negative 3. Our range would not change, it would still be all reals. And then similarly, if you have negative log base 5 of x minus 2, now since we are dealing with log of base 5, our values are going to change ever so slightly. It's still going to look like, well, if the negative wasn't there, it would still look like this. The difference being, well, 1, 0 would still be there. But when the base is 2, we went over 2 and up 1. Well, from 1, 0, the next coordinate out would be 5, 1. The next coordinate after that would be way over here at 25, 2. And what I'm talking about here as far as these coordinates are concerned would be as if this was just log base 5 of x. Next coordinate on this side would be at a negative 1 for the y value. The x value would be 1/5. If we change our number to, say, a 16 down here, well, now it's still 1, 0 is going to be a value, but it's then going to be 16, comma 1. And our other number there would be 16 squared, which is 256, comma 2. And this coordinate, instead of being 1/5, comma negative 1, it would be 1/16, comma negative 1. And like I said, and that's just if it's just log whatever base and then x. Your numbers change by what the base is. Okay, so with this one, because it has a negative sign and also a minus 2, remember this minus 2 is going to shift it to the right 2. The negative out here is going to flip it over the y-axis. So in our graph, instead of our asymptote being at 0, it's going to be to the right 2. Instead of it crossing at 1, 0, like it usually does, it's going to be shifted to the right 2. So it is going to cross at 3, 0. And then the next coordinate, if we're talking if it's log base 5, instead of being over 5 and up 1, it is going to go over 7 from the origin. and up 1. And so now your graph is going to look like that. All right, moving on to the next bit of information. Oh, but wait a minute. That would be as if this negative sign was not here. Since the negative sign is there, that's going to flip this graph this way. And this one won't be there. Shifts it all to the right too, and then we have to flip it over the y-axis. So instead of going over from this point, from our asymptote over 5 and up 1, we'd have to go over 5 and down 1. Okay, moving on to some properties of logarithms. Anytime you have a logarithm with whatever base, and it's 1 here, it is saying b to what power is equal to 1. And that would be 0. The second one here says log base b of b. So now that's asking b to what power is equal to b. And that is 1. Next one is b to what power is equal to b to the x. And so we would have an answer of just x. Or you can look at it as the log base b and b to some power are inverses of each other. So inverses go away, which leaves you with just x. Okay. Which then applies to this next one, x log base b of b. That log base b and b are inverses, so they go away, and you're left with just x. Now you can also look at it another way. Log base b of b from this property right here says that that is 1. So now we have x to the first power, and anything to the first power is just that thing. Now, some examples of things. Log base 5 of 1 over 25. It's saying 5 to what power is equal to 1 over 125. And we all know that 5 to the third is 125. So to get it to be the reciprocal, log base 5 of 1 over 25 is equal to a negative 3. Our next one is log base 3 of 27. That is saying 3 to what power is equal to 27. And that would be 3 to the third. So log base 3 of 27 is equal to 3. And then our final one of this part log base 2 of 16. So here we're saying 2 to what power is 16? And that would be 4. Now, a couple other things about logarithms. There are a couple of special ones that you need to remember. One is called a common logarithm. A common logarithm, the base is 10. And so it would be written like this, log base 10 of x. But because it is a special one, the reason it's special is because the base is 10, and that's our numbering system. Because we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 10 then makes us change to then a 2-digit number. So that's why it's base 10. So a common logarithm, log base 10 of x, we would not write that. Instead, we would just write log of x. When you see this, do not assume that this is a 1 down here because it's not. It is a 10. The second type of logarithm is a natural logarithm. And in natural logarithm, the base is e. And if you recall from section 1 here, e is approximately equal to 2.71 and stuff. And so, if the base is e, it would be written log base e of x. But just like with a common logarithm, it is not written that way because it is something that's used more often. This one would be ln of x. And these two are both calculator friendly. There should be a button on your calculator for this, and there should be a button on your calculator for that. Look for log x and or just log and look for ln. Understanding that when it's log, that the base is 10, and when it's ln, the base is e. Now in using those, if we had log of 10, that would equal 1. If we had log base 10 of 10 to the 6.2 power, that would just be 6.2. Because log base 10 and 10 go away, and so you're left with just 6.2. And this wouldn't have to be written there. Same thing could happen as if you had ln of e to the 6.2. Then our answer is still going to be 6.2 because ln and e, they cancel each other out because they're inverses of each other. One final example would be ln of e to the 705. And that would equal 705. And here ends the second lesson of chapter 3. So you may now start with the work on it.